Welcome back to the Learning Studio. You're watching our mathematics series, where we uncover the powerful ideas shaping science, technology, and artificial intelligence. If this is your first time here, don't forget to follow us by clicking the link below, and the full playlist is also in the description, so you can explore each episode in order. Today, we're entering the world of functional analysis, a branch of mathematics that studies infinite dimensional spaces. It may sound abstract, but as you'll see, it's a key player in neural networks, kernel methods, and modern AI. Imagine you're studying vibrations on a guitar string. The shape of the vibration isn't just a single number, it's a whole function. Now imagine doing the same for sound waves, heat distributions, or probability densities. Functions themselves become the objects we want to study. But here's the challenge. Functions live in infinite dimensional spaces. To make sense of them, mathematicians built functional analysis, the study of vector spaces of functions and the operators that act on them. This field lets us stretch linear algebra into infinity. Core concepts explained simply. Here are the essentials. Vector spaces of functions. Just as vectors can represent positions, functions can be thought of as points in huge, infinite dimensional spaces. Hilbert spaces. These are special spaces where we can measure angles and distances between functions, just like we do with finite dimensional vectors. Hilbert spaces give us the foundation for quantum mechanics, signal processing, and neural networks. Operators. In functional analysis, instead of matrices acting on vectors, we study operators acting on functions. These generalize the idea of transformations to infinite dimensions. Kernel methods. In machine learning, kernel tricks allow algorithms like support vector machines to operate in high or infinite dimensional spaces, powered directly by functional analysis. In short, functional analysis is infinite dimensional linear algebra, the language of functions, spaces, and transformations. Why it matters in AI and technology. Functional analysis is not just theoretical, it's everywhere in modern technology. In neural networks, Hilbert space theory helps us analyze convergence and generalization. In machine learning, kernel methods let us project data into higher dimensions where it becomes linearly separable. In quantum computing, Hilbert spaces are the stage on which quantum states live. In signal processing, operators and function spaces describe how filters, transforms, and systems work. It provides the rigorous framework for dealing with problems that are too large or even infinite for standard linear algebra. So functional analysis is where mathematics stretches beyond the finite. It's the bridge from linear algebra to infinite dimensional spaces, powering AI, physics, and engineering alike. In our next episode, we'll turn to Fourier analysis and wavelets, the tools that allow us to decompose signals into frequencies, analyze images, compress audio, and extract features. If functional analysis is the theater, Fourier analysis is one of its most spectacular performances. Don't forget to follow us by clicking the link below and check out the full playlist in the description. Each step of this journey reveals how mathematics shapes not just theory, but the technologies we use every single day.